fellow STEM research and honorable scientific communities. I'm Deniz Ezgi Varol, a chemical engineer and graduate student at Marmara University in Turkey. I'm working on a major project of preparation of metallophthalocyanine-based photoelectrodes for photoelectrochemical hydrogen production systems, and I'm so pleased to share with you part of my results. First of all, I would like to tell you about the content of my presentation. First, I will talk about the basics of the subject. Here, I will talk about the concept of energy, and secondly, I will go into the details of hydrogen energy. Thirdly, I will deal with the subject in a more specific way and talk about photoelectrochemical hydrogen production, technological development, industrialization, and increase in the world population, rapidly increasing the demand for energy. Energy, which is the basic input in the production, is a necessary element for increasing the welfare level of societies and is used in the almost every field of daily life. In short, energy, which is defined as the ability to do work, can be found in different types such as mechanical, heat, electrical, chemical, and nuclear, can be transformed from one type to another with the appropriate methods. For the future, it's possible to say that, according to the research conducted by the International Energy Agency, renewable resources are expected to surpass coal in 2025 to become the largest energy sources worldwide and lead the electricity sector in particular. The use of hydrogen specifically and by extension hydrogen is gaining momentum in the current global energy transition framework. Green hydrogen has significant potential in the future renewable-based power generation, acting as a buffer for renewable generation. The first step of the experiment is electrode preparation. There are many methods you can use at this stage, such as chemical bed deposition, sol gel, and electrochemical deposition. We use the electrodeposition method here. In the preparation of photoelectrodes used in photoelectrochemical hydrogen production methods, basically two different strategies are used. The first of these methods, after the photocatalyst is synthesized by different methods, the photocatalysts are applied on various substrates as chemical or physical vapor deposition, dip coating, cast film coating, spin coating, or Dr. Blade. It's covered with the technologies such as coating with the so-called smearing. Photoelectrodes prepared in this way are then used in package systems. The second of these methods, photocatalyst system, is synthesis on substrate and used as photoelectrode. The second method is more preferred because of its advantages, such as synthesis and electrode preparation together and preparation of more homogeneous, pure and controlled electrodes. The three-electrode system consists of a working electrode, counter-electrode, and reference electrode. The reference electrode's role is to act as a reference in measuring and controlling the working electrode potential without passing any current. The reference electrode should have a constant electrochemical potential at low current density. The most common lab reference electrodes are the saturated calomel electrode and the silver chloride electrode. In the three-electrode configuration, the only role of the counter-electrode is to pass all the current needed to balance the current absorbed at the working electrode. The counter-electrode will often swing to extreme potentials in order to accomplish this task. Saturated calomel electrode was used as the reference electrode, and platinum wire was used as the counter-electrode in this work. The electrolyte contains soluble salts of metals in the structure of the composite: water, ethylene diamine tetraacetic acid, in short ETA, zinc phthalocyanine, and graphene oxides. These are mixed with each other in certain volumes. The pH of the solution was adjusted with the help of sodium hydroxide. The pH was brought between 8.5 and 8.7. Finally, the obtained black solution was transferred to the three-electrode experimental setup. During the process, thin films were generated by using electrode opposition with the cyclic voltammetry. First of all, the ITS to be used as the substrate. The washing procedure was briefly as follows. The first ITS are taken into the glass beaker and washed with the detergent water. Secondly, washed with ethyl alcohol and mixed in an ultrasonic bath. And finally, the procedure is complete by washing with the distilled water. The three-electrode system was set up. For this, the electrolyte was placed on the bench, saturated calamine electrode was used as the reference electrode, and PTY was used as the counter electrode. These electrodes were washed with distilled water before use. After all electrodes were connected to the system with the help of crocodiles, the cyclic voltammetry method was started at the scan rate of 100 millivolts per second for 10 cycles with voltage range from minus 1.6 volt to zero point 0.7 volts. In the meantime, it's very important that the ends of the metal crocodiles do not come into the contact with each other. Otherwise, the system gives overload. After the cycles were complete, the produced electrodes were annealed in a horizontal tube furnace at 250 degrees Celsius and in an argon gas environment for 1 hour in order to obtain a smooth and homogeneous surface. Before starting the experiment, the produced electrode was covered with the silicone. The purpose the purpose here was to prevent electron-hole recombination. Then, with the help of silver paste, the wire was adhered to the conductive part of the electrode. The photoanodes produced for analysis to be carried out in light and dark environments were immersed in sodium sulfate and sodium sulfide sacrificial agent with a pH value of 13. The intensity of the light coming to the photoanodes was adjusted to 1000 milliwatts per centimeter carry, in other words, to 1 sun using a radiometer. Figure 4.1 shows the linear civil voltammetry curves of annealed composite material. It's possible to say that optimum annealing temperature leads to larger particle size, developed crystallinity, and better crystal orientation for the thin film electrodes. In this study, the appropriate annealing temperature was determined as 250 degrees Celsius, which is the temperature that reduces the recombination rate of photoinduced charges. All linear experiments were carried out in light environment. Under air mass 1.5 global solar light illumination, a light was turned on and off every 100 millivolts. Here we see the chronoperimetry graph of the three electrodes. Chronoperimetry involves the study of the variation of the current response with the time under potentiostatic control. The instantaneous photoresponse of photoelectrodes were worked by applying chronoperimetry tests for switch on and switch off conditions in 50 seconds intervals. According to the figure 4.2, reduced graphene oxide, azido, cadmium, zinc, nickel, sulfur, selenite, zinc, phthalocyanine gave the highest photoresponse, which is 7.3 milliampere. At the same time, this structure has high stability and low recombination. When the electrode with covered cobalt phthalocyanide was examined, it was determined that the photocurrent density was 5 milliampere. This value is 1.46 times less than the current density created by the zinc phthalocyanine electrode. Thank you very much for listening to me. If you have any questions, I'll be happy to answer them.